The blue sky and a red sunset are the same trick, happening at two different distances. Watch the sun stay white while the air steals its blue light. At noon, that stolen blue reaches you from every direction, so the whole sky glows blue. Near sunset, sunlight takes the absurdly long route sideways through the atmosphere. So much blue gets scattered away that the beam reaching your eyes is left orange and red. Same sun, same air, completely different result. And here's the part I want to hold back for a minute. Why does the air pick on blue? Air looks transparent. You can stare through a room full of it without everything turning orange, and the molecules floating around are far smaller than anything you can see. Somehow those tiny invisible molecules can sort sunlight by color, flinging blue sideways while mostly allowing red to cruise straight through. I got this wrong the first time because I pictured the atmosphere like a weak blue filter. That picture breaks immediately. A blue filter would make the sun look blue too, which is very much not what happens. The useful picture is stranger. Think of every molecule as a tiny light-powered antenna. White sunlight shakes it. The molecule sends some of that light back out, and the amount it sends depends dramatically on the light's wavelength. How dramatically? Well, doubling the wavelength changes the scattering by a factor of 16. That tiny rule is doing basically the entire sky. That factor of 16 comes from treating one air molecule like a tiny driven antenna, and this is where the invisible air finally gets a body. Light is an oscillating electric field. As the wave passes, that field tugs the molecule's electrons one way, then the other, over and over. The electrons are attached to the molecule, so they don't leave. They wobble. A wobbling electric charge radiates light, which means the molecule sends a little wave outward in new directions. That's scattering. No photon needs to hit a molecule like a tennis ball hitting a wall. I used to imagine exactly that, by the way. Tiny billiards in the sky. Cute. Deeply unhelpful. The important bit is speed. Blue light has a shorter wavelength than red light, so its electric field changes direction faster. That faster shaking makes the molecule radiate much more strongly. For particles far smaller than the wavelength, the scattered intensity scales like 1 over wavelength to the 4th power. Honestly, that 4th power is doing suspiciously heavy lifting. Compare blue around 450 nanometers with red around 650. The ratio is 650 over 450, raised to the 4th, which is about 4.4. A molecule scatters that blue light more than 4 times as strongly as the red. Great, we've caught air favoring blue. Except this creates an annoying new problem. Violet has an even shorter wavelength, so the rule says violet should win. If shorter scatters more, why isn't the sky violet? Violet really does scatter more. The equation survives. Our eyes and the sunlight arriving here quietly rig the contest. Start with the sun. It sends out a broad spread of visible wavelengths, though the amount isn't perfectly equal across every color. Then the upper atmosphere removes some of the shortest wavelengths, and the remaining violet still has to be noticed by your eyes. Human vision uses 3 kinds of cone cells, loosely sensitive to long, medium, and short wavelengths. The short wavelength cones do respond to violet, but they're much more useful around the blue part of the spectrum. Our eyes are also far less sensitive at the extreme violet edge. Add everything together, and the scattered mixture looks blue, with a little green and violet folded in. It isn't the pure blue of a laser. If you measure the sky carefully, its spectrum is a lumpy spread. Your visual system turns that spread into the color label blue. Also, the sky near the horizon often looks paler because scattered light travels through more air before reaching you. It gets scattered again, and larger particles mix in more wavelengths. The clean blue overhead gets washed toward white. So the answer isn't one smug sentence about wavelength. It's a conspiracy involving the sun's spectrum, molecular scattering, the atmosphere, and the response curves inside your face. Fine. Blue wins. But we still haven't explained how light scattered by molecules all over the sky reaches you as one smooth glowing dome. Pick one tiny patch of empty-looking sky. Where exactly is its blue light coming from? That blue ray began as ordinary sunlight traveling somewhere else. This one was headed past you, crossed a molecule in that patch, and got redirected into your eye. Move to the next patch, and the geometry repeats. Another molecule another sideways turn, another blue ray arriving from another angle. Millions of these microscopic reroutes make the atmosphere behave like a glowing screen wrapped around you. Keep your eye on one molecule. It doesn't spray equally in every direction. Rayleigh scattering has a directional pattern, stronger forward and backward relative to the incoming light, and weaker at right angles for a particular polarization. Sunlight contains mixed polarizations, so the real pattern averages into a smooth two-lobe shape. This leaves a clue you can actually photograph. Skylight is polarized most strongly about 90 degrees away from the sun. Rotate a polarizing filter and parts of the blue sky darken. Some insects use that polarization pattern as a compass, which feels unfair. I lose my bearings inside large supermarkets. Now pull back. Every incoming white ray loses only a tiny fraction of its blue at each encounter. The direct sun can still look nearly white around midday because its path through the atmosphere is short. Meanwhile, the enormous number of molecules off to the sides collectively supplies blue light from the rest of the sky. Distance is the control knob. Tilt the sun lower, and its beam must cross more air before reaching you. How much more? Near the horizon, the path can be roughly dozens of times longer than the straight overhead route. That's when a gentle blue leak becomes a full color heist. That long path is the whole sunset switch. Picture the atmosphere as a thin shell around Earth. Thin is relative here. It's deep enough to breathe in and make weather, yet compared with the planet, it's like the skin on an apple. At noon, sunlight drops through a relatively short slice of that shell before reaching you. Near the horizon, the ray skims sideways through it. A little geometry turns the thin shell into a very long corridor. As the beam crosses that corridor, blue scatters first and most strongly. Some green goes too. The direct beam becomes yellow, then orange, then red. This gives us the frame worth keeping. The blue sky is the light removed from the sunset beam. Trace one incoming white ray. Every blue branch heading into the sky corresponds to less blue continuing toward the setting sun. The two colors are complementary parts of one transfer, and yes, the sun itself often looks yellow or red while the surrounding sky stays blue because you're comparing direct transmitted light with scattered light arriving from elsewhere. Different paths, different mixtures. Now for a detail that stops this explanation from becoming too neat. Molecules alone can produce the basic sunset, though real sunsets are packed with dust, smoke, salt, water droplets, and pollution. Those particles can be comparable to the wavelengths of visible light. Once that happens, the clean 1 over wavelength to the fourth rule stops being the right tool. Bigger particles scatter colors more evenly and strongly forward. So why do some hazy sunsets blaze red while others collapse into a dull white smear? The difference is particle size, amount, altitude, and where the light has room to travel after scattering. Tiny molecules give Rayleigh scattering, with that fierce preference for short wavelengths. Larger aerosols move us toward me scattering, where wavelength matters less and forward scattering becomes much stronger. Lots of water droplets scatter red, green, and blue fairly evenly, which is why clouds usually look white or gray instead of electric blue. A moderate layer of fine dust or smoke can remove extra blue and green from a long sunset beam, leaving intense reds. Too many particles, though, and they scatter or absorb so much light that the colors flatten and the whole thing turns murky. Volcanoes can produce spectacular sunsets by placing fine particles high in the atmosphere, where sunlight can cross huge distances through them. Wildfire smoke can do something similar, although the view comes with an obvious and awful trade-off. Here's a nice diagnostic. A clean molecular sky produces a saturated blue overhead. A hazy sky often fades pale around the sun because forward scattered white light piles up there. Watch the sun's neighborhood become a bright washed out disk, while the sky farther away keeps more color. This is also why a cloud is a terrible place to search for the wavelength to the fourth effect. Its droplets are thousands of times larger than air molecules. Scale changed, so the scattering rule changed with it. We can now explain blue days, red evenings, white clouds, and ugly beige haze using the same basic move. Light meets particles and changes direction. There's one last test, though. If Earth's atmosphere is responsible for the color, what would the sky look like from somewhere with completely different air? Change the atmosphere, and the entire color story changes. On the moon, there's essentially no atmosphere, so there are almost no molecules to redirect sunlight into your eyes. The sun can be blazing overhead while the rest of the sky stays black. Mars has a thin atmosphere loaded with fine dust. During the day, that dust makes much of the Martian sky look reddish or butterscotch. Near sunset, forward scattering by tiny dust particles can concentrate bluish light around the sun, giving Mars a blue sunset. Earth's familiar colors run backward. That's such a good cosmic prank. On Earth, meanwhile, the exact shade above you is a live measurement of molecular density, aerosols, humidity, solar angle, and your own visual system. The simple rule survives underneath all that mess. Small air molecules scatter short wavelengths much more strongly, so sideways, light looks blue. A long path removes those short wavelengths from the direct beam, so sunsets lean red. I know that sounds obvious once the diagram is sitting there. It took me 3 attempts to stop thinking the air was somehow dyed blue, so no judgment. Next time the sun is low, point at the red beam with your eyes, then look 90 degrees away at the blue it lost. You're seeing one stream of white light separated across the whole sky. And here's the thing that still bugs me, in the fun way. Our atmosphere is only a thin, transparent shell, almost nothing beside the size of Earth, yet every clear day it builds a planet-sized color display from particles too small to see. Change those particles slightly, and the sky becomes white, black, orange, or Martian blue. So somewhere out there, under an atmosphere we haven't sampled yet, there's probably a sky color our intuition is completely unprepared for.